Here's a procedure for finding the regions of increasing and decreasing for a function using the first derivative. First, we're going to find the domain of our function. Then, I'm going to take all the critical points, all the discontinuities. We're going to carve up the domain using those points. Now, if I take one of these regions, I take a point in the interior, I apply the first derivative to that point. If the value is positive, then we're going to be increasing on the entire region. If the derivative is negative, we'll be decreasing on the entire region. And that's all we need to do. Let's look at some examples. My first example, f of x equals x cubed minus 6x squared. This is a polynomial, so its domain is all real numbers. So we're going to take the derivative and look for critical points. Take the derivative, I get 3x squared minus 12x. I factor that, I get 3x times x minus 4, and I set that equal to 0. So we'll have critical points at x equals 0 and x equals 4. These are going to be critical points where there's a horizontal tangent line. Now I take our domain, all real numbers, okay, put it all written as a box. Then I'm going to mark off at x equals 0, x equal to 4. To find increasing and decreasing, we're going to apply the derivative to 1 point from each region. So the points that we'll use will be minus 1, 1, and 10. Put minus 1 into the derivative. What's going to happen? Well, I'm going to have 3 times minus 1 times minus 5. So that's going to be positive, negative, negative gives me a positive. I don't worry about the actual number. I just have to worry about the sign that comes out. So I have a positive. So I'm increasing in my region going up to 0. Okay, 1 is in the region 0 to 4. Put that in the derivative. What do we get? I'm going to have 3 times 1 times minus 3. That's a negative. So I'm going to be decreasing in my middle region. For my final region, 10 is in there. 10 is bigger than 4. So what are we going to have? I'm going to have 3 times 10 times 6. That's a positive. So I'm going to be increasing in this far region. Next example, f of x equal to 1 over x squared. Okay, we can rewrite that as x to the minus 2. Here, when I check the domain, since I can't divide by 0, the domain will be all real numbers except x equal to 0. At that point, we're going to have a vertical asymptote. So when we check for increasing and decreasing, that's going to be a possible point where we can switch from one to the other. Now, we take our derivative. What are we going to get? Bring the exponent down, gives me a minus 2. New exponent's minus 3. So I can rewrite that as minus 2 over x cubed. We're going to check 1 point in each region, split by the vertical asymptote. So I'll use 1 and minus 1. If I put a 1 in there, I get a minus 2. So we're going to be decreasing on that side. If I use minus 1 cubed is minus 1. So a 2 comes out. That's positive. So we're increasing on this side. If I check this against the graph, notice our graph looks like this. So as I go from left to right, if I'm less than 0, this is going to keep moving up. So we're increasing there. As I go from 0 to the right, this is going to keep going down. So we're decreasing there. So our picture matches our calculation. And note, the whole point of this one is you have to make sure you get your domain in order before you take your derivative. With this business of increasing and decreasing worked out, we now have first derivative test. So what does this say? I'm going to have x0, critical point of f. That means f prime is either 0 or undefined. I'm going to check the sign of the derivative on each side of x0. If the derivative goes from positive to negative, we're going to have a relative maximum. So the way you think of that is, if I'm going from positive to negative, the function's going from increasing to decreasing. So we're going to have a peak at the top at our critical point. On the other hand, if I go from negative to positive on each side of my critical point, we're going to have a relative minimum. In that case, we're going from decreasing to increasing, and And then at the bottom of the bowl is our critical point, which will be a relative minimum. Let's look at an example. So I'll go with our old example of f of x equal to x cubed minus 6x squared. So we have critical points at 0 and 4. So we'll mark them off. And what do you notice? Well, the procedure was, if you wanted to sign in any of these regions, it was enough to check 1 point. So here, we're going to go from, at x equals 0, plus to minus, which says I'm going from increasing to decreasing, so I have to have a relative maximum there. If I look at the graph, at 0, we have our relative maximum. If I put that inside of a circle, that's just going to look like a maximum for the region we're looking at. Now at 4, we're going to go from negative to positive on each side of 4. So what's going to happen there? I'm looking at a relative minimum. If I take a look at the graph, here we are at 4, and you put a circle around 4, we're going to have a relative minimum there. So that's our first derivative test.